In this video, we'll continue our discussion of curvature, talking about the components of an acceleration vector. So when we're accelerating, we actually have two different components. Let's take a look at our picture. We actually have our acceleration vector right there that I just covered up. So right here, acceleration vector could be broken down into two different components. It's not right to say x and y components because what we're going to actually break that down to won't be just x and y. It's going to be like a vector that has different components that way that could be turned different ways. So instead of saying like the x component and the y component, we could also describe acceleration in terms of its tangent vector and its normal vector. That I know that there's some vector here that is the quote-unquote x component, if you want to call, or y. It's really arbitrary which one you would want to pick, but it's how much of acceleration moves in the direction of the tangent vector. And then also the normal vector, we're going to try to figure out how much of the acceleration moves in the direction of our normal vector. Okay, so let me run you through some theory real quick. We'll begin again with this fact, which means we can go ahead and solve for v. Also recall that the magnitude of v is also the change of arc length over time. So if we take that equation that we have there, all we're doing is replacing this with that v. So we replaced it there. And then we're going to take the derivative. So if I take the derivative of velocity, I get acceleration. Then I'm going to go ahead and take the derivative of what we called velocity. This is a power rule. Sorry, not product rule. Keep doing that, product rule. So it's the derivative of the first one times the second, and then the derivative of, keep the first one derivative of the second. Right? This next step looks a bit tricky, but we can actually take dt, ds, and I can use the chain rule from Calc 1 to do dt over little dt times, or we'll call it, let's say I'm going the wrong way. So if we could start with dt, I can actually break that down to dt over ds times ds over dt. So that's what they did from here to there. We know those are the same thing. Okay, and then we have one last step, and you can see that we're going to have this part's going to go by itself, and then actually this is that velocity squared. dt ds is the same thing. Remember that dt ds was the normal vector. It was the direction of the normal vector anyway. So since I know it's the direction of the normal vector, I can say, hey, it's the normal vector, and then the magnitude of my normal vector, I could just call it that k there. So we have two different components. That kappa is, I believe it is, curvature. So now we identify the normal and tangential components of each of the acceleration. So remember, this is going to give me how much of acceleration is moving in the tangent vector direction, and then how much of our acceleration is moving in the normal direction. So we could break acceleration into something times n plus something times t. Those are the components in each direction, but if I add them together, I get the vector themselves. We have the a sub n is equal to this, and that we have a sub t is equal to that. Right? The tangential component of the acceleration in the direction of t is the usual acceleration of an object moving along a straight line. The normal component in the direction of n increases with the speed and with the curvature. So higher speeds on tighter curves produce greater normal accelerations. Think about that for a while. It definitely makes sense. All right, let's try an example. All right, there we go. Sorry for the curving back and forth there. I was looking at my notes versus moving this. Okay, so find the components of the acceleration on the circular trajectory. Okay, so we have this problem. So the first thing we're going to do is find, given the formula, we have, let's write down that again, a sub n is equal to v cross a, that's acceleration, over magnitude of v. Okay, so we need r prime and r double prime. So r prime, I'll go ahead and write the, we'll do tangential in a moment. Okay, so this is going to be negative 3 pi sine pi t. And then we get the same thing here, but it's 3 pi cosine pi t. We also need r double prime, which is going to be negative 3 pi squared sine pi t, or cosine pi t, sorry. Cosine pi t. And then we got negative 3 pi squared sine pi t. Right, we have to cross those two things. So we're going to add z components and go ahead and cross. If we have to find the magnitude, oh, we don't have the angle. Okay, so I was going to use that formula, but we don't have theta, the angle between the two vectors, so we won't do that. Okay, so I have that. I'm going to go ahead and just use, I'm going to jump to the parentheses, so if you need to do the determinant definition and go through that, please do. If not, I'm going to write out just each part. Alright, so it looks like we just get a k component, and it's going to work out in our favor. It's going to be, so 3 squared, okay, so negative 3 times negative 3 is going to be a 9 pi cubed, so we're going to end up with a 9 pi cubed there. Okay, so follow your cross product. I'm going to save some video time by not doing that. Let me double check that really quick. I got 9 pi cubed sine squared plus 9 pi cubed cosine squared pi t. All those are the same, so we can use the Pythagorean triple just to get that, right? To find the magnitude of that, so the magnitude of v cross a is going to be that exact value, 9 pi cubed. All right, and then over v, which was r prime, so v magnitude is going to be a 3 pi. Yeah, and you could check that out if you'd like. So if it's over 3 pi, then the a sub n is equal to the magnitude of one divided by the other, so we get 3 pi squared. All right. Okay, for the other one, recall that ds over dt is equal to the magnitude of vt. We stated that above. So if that's the case, which is constant, right? Because that's this. It's constant. So what that tells me is if I take the derivative again, we get 0. If it's constant, right, then the derivative of again would just be 0. So a tangential is 0. So there are our two answers. All right, we got one more example of this. A construction company is considered building a road that follows the parabolic, I think that's a word, maybe trajectory of that curve. There's the picture there. For -2 to 2, through a sharp bend, find the tangential and normal components of the acceleration of the car. All right, so you can see how that works there. We have acceleration in the green, and then we have our components in blue and red that tell us each one. Okay, so let's start with finding. We have that. Let's go ahead and find our r prime, which is going to be our velocity. Okay, r prime is 1, 2t. All right, we also need our double prime, which is going to be our acceleration. And we get 0, 2. That's nice. Okay, so that tells me that we want to express, our goal is to express a in terms of some a n plus a t t. That's what we're trying to get it into each component. So let's go ahead and find our t of t, our tangential unit vector. Remember, that's going to be r prime over its magnitude, so we get 1, 2t. Its magnitude is going to be 1 squared plus 2t squared under a radical, so that is 1 plus 4t squared. All right. To save you some time, I'll do this for you. The n of t over, just n of t. If I take the derivative and do that again and divide, okay, I get negative 2t, comma 1, over that same thing. This is just me skipping the heavy derivatives. So you would need to take the derivative of this and then divide by its magnitude to get n. So that's what we have there for each one. Okay, so we have two ways to go about this. I'm gonna do one way, and then we'll check it with the other. There's I would probably just take this first way every time. So we now have two ways to proceed. We know that a sub n, remember, is going to be the acceleration dotted with the n vector, because it's how much of acceleration is going in the n direction. So if I just use what I have here, I got 0, 2 times, or dotted with, that vector. Remember, the whole point of a sub n is the magnitude in the direction of n. So all we have to do, if I want how much acceleration is in n, I'll just dot it. All right, so we get negative 2 over the square root of 1 plus 4t squared. But if I take this dot, the x components go away, so we get a nice pretty 2 over 1 plus 4t squared. All right, a sub t is that same idea, except for it's going to be acceleration in the direction of t. So I'm getting, I guess, a little lazy with my arrows there. So it's 0, 2, dotted with t, which is 1, comma 2t, over the square root of 1 plus 4t squared. Notice the 0 is going to make that go away, and I got 4t over the square root of 1 plus 4t squared. You can check this. We know that a sub n is we have it written right here. So I could just throw those in front. 2 over the square root of 1 plus 4t squared times n vector, plus 4t over the square root of 1 plus 4t squared t vector. You could plug in n and plug in t and make sure it works out to get, this should be 0, 2. That would be a good check. So this is how we take some acceleration vector and we can actually break it down to its components. But remember, it doesn't make sense to say x or y, because that acceleration vector is not going to always be pointing in a way to grab x and y. It's going to be, it has components, but it's a component in the way of tangent vectors and normal vectors.